So I'd just like to say to anybody, to the people here, thank you for coming to this presentation of mine, and thank you for the invitation from Professor Nymark, and thank you, Irina and Dennis, and all the other people who are helping this afternoon in London, where I'm at the moment. It's 10 o'clock in the morning, and I'm very, very happy to be here. Okay, I Oleg, would you like me to start the presentation now?
If you're asking us any question, it's up to you. We could ask you if it's not too disturbing for you during your presentation, but it's possible also after your presentation. It's your choice.
Absolutely. I have a tutorial to give at in 1 hour's time, but up until that moment, I have no problem whatsoever, and I'm very happy. I have 65 slides, which is a lot, but I don't hope what I hope to do is talk more generally and not go through every single derivation, and mainly to give people an overview. And people can ask questions as we go along. But you know, if I don't get to the end of this presentation today, this is a series of 7 presentations, and people can feel happy to ask questions, and they can send me questions in between presentations. I don't mind answering. I want to make this easy and happy for people.
You are very kind. It means that we have opportunity to ask you during the presentation.
Absolutely, absolutely.
And please,
if you ask me lots of very deep, no, thank you, Oleg. If you ask me lots of very deep philosophical questions, I think I might take a lot longer. So, so this morning I'm just going to give an introductory talk about elastoplastic waves in very general terms, and discuss loading platforms. Again, very general terms. There is a lot of detail you can find in the scientific and technical literature, so this is very much an overview. There is a review article from 2005, so 16 years ago, that I was a co-author of, and I've shared that with Oleg, and you are very welcome, I hope, to have copies of this and read it at your leisure if you want to look in a little bit more depth. So when I start talking about loading platforms and waves, I ask students and my colleagues, what is mechanical strength? Well, you put a load, you put a force on something and it supports it. That's the definition of strength. Another definition of strength is the ability to maintain shape, because we know that stress, the load, and the deformation strain are linked. And strength is basically how much a force changes the shape of a material. And there was some 17th century English scientist Robert Hooke. He came up with Hooke's law, which X represents the extension of a spring or an object, and F represents force, and K is a constant for the material, sometimes called the strength, sometimes called the spring constant if it's a spring. So he came up with the change in extension was some constant dependent upon the material multiplied by the change in force. Thomas Young came along in the 19th century, early 19th century. Again, he was based in London at that particular time, and he came up with a thing that today we call Young's modulus. He did not call it that himself, other people gave it that name. And he said, in a version which hopefully people will be more familiar with, that Young's modulus E is a change in stress divided by the change in shape, the change in strain. Now, Young's modulus is a particular way of measuring strength, a particular value, and it was based upon rods and wires of material that were put under load. Because engineers and scientists are interested in materials of different shapes, then we use other versions of definition of strength. There is shear modulus, the ability of a load to move a sample Normally, we would say laterally. We think of forces generally working in the direction of gravity from the top to the bottom, but you can try to pull things to one side. There is also a version of strength which we call the bulk modulus. And this is when we're looking inside the material at the interior, and we're looking at waves and forces moving outwards through the bulk of the material. These names just very simply reflect the type of loading we're talking about. Other very simple factors that I do not wish to repeat things you know terribly deeply is due to a French engineer, Poisson, and he came up with a Poisson's ratio represented as a change in lateral strain divided by what happens when we change the longitudinal strain. So those are some very broad definitions of mechanical strength. Now, if these values were constant for all materials, we would not be having this talk today, because life would be extraordinarily simple, but probably life needs a certain level of complexity, so things change. So when we think about a load being applied to a material, and particularly a load that's being applied dynamically, the strength is propagated through the material in the form of a wave. And just as there are different types of strength, there are different types of waves. There are those which compress the material, those which try to extend the material, we'll call them tensile waves. We have waves that try to move material laterally to what we consider the normal loading direction. Those are shear waves. And there are waves which tend to propagate along the surface. There is a paper I provided to Oleg where my colleague Stephen Wally and my former supervisor, Professor John Field, talk about different types of waves. And please, again, read that article if you can. It's a very good summary. If we think about wave speed and strength, we feel there must be a connection between the two. So in a very simple way, and here I am basing my explanation on the work of David Tabor, who was one of the founders in the Cavendish Laboratory of Western European studies on friction, modern versions of friction. If we look at the potential between three atoms, so here, very standard representation, the yellow spheres, the yellow circles are atoms, and the line represents the bonding between them. And what we see at the top is there is an atom, and it moves, in this case, in the right-hand direction towards that atom. It then moves backwards to the middle, and then it moves off. So it oscillates between the two atoms. It vibrates between those other two outer atoms. So if we want to approach that simply, we can claim it's a simple harmonic oscillator. And as a result of that, we have a particle which moves and then stops at the limit of motion from the midpoint, and then it gets accelerated by the repulsion from the atom it's nearest and the attraction of the atom it's furthest away from. And so we have this oscillating object. Very simple equation. Velocity x dot is 0 at the limit. The acceleration is minimum at the limit. The acceleration is maximum at the limit, and we can link those two, remembering that position, velocity, and acceleration have both magnitude and direction. So very simple equation, nothing that should cause people too much difficulty. If we consider it as a oscillator, that oscillator has a time period, and we can look at what is the frequency of oscillation of a simple harmonic oscillator, and you will have this equation 2 pi and the mass of the system divided by k, and k is basically a measure of the force of those springs. It's the spring constant that we have between those atoms, and that's square rooted. Now the next part requires an assumption. It's not a very big assumption, but if we assume that the maximum impulse is transferred at the maximum point of motion, i.e. a quarter of the cycle, then we can say that the time for maximum stress transfer, the maximum force between the oscillator and its neighbor is a quarter of the time cycle. So there, I've just taken that, divided it by 4. And then I'm going to combine it. And what I'm going to get is time equals 2 pi divided by 5.7 m over k to the half. And 2 pi over 5.7 is approximately 1. You can tell me it's not exactly 1, and I will tell you you're right. You can tell me that there are other ways of deriving this equation, and again, I will agree with you that you are correct. This is just a version that I'm presenting in a very simple way. So if we think about velocity, velocity is distance by time, which is velocity of a wave representing as movement of stress. The velocity of the wave is distance divided by time. Well, what is the distance? Well, this is this distance x between the atoms. And what is the time? Well, we've talked about the time it takes to transfer from more or less zero stress to maximum stress. We can combine those terms. So x, we've got this x step in the middle. Velocity equals x brackets k over m to the half. That is the time expression. Now, what is x? X is a distance. Now, we can express distance in terms of density if we remember to basically separate variables. So what we've done here, we've taken that thing and we've separated it into a density term and a thing called k over x. Okay, so what is this saying? Well, x cubed over m is density. That's that. K, or force divided by distance. Force and distance, that is force being applied and distance, or strain if you want to call it, or motion in the sample. So that is basically strength. So that term, k over x, is a strength term. The ultimate outcome of doing this type of analysis is to say that the velocity of the wave is equal to a strength term. In this case, it's the bulk modulus, because those atoms were moving in the bulk, divided by the density of the material to the power of a half. Now, in this little introductory talk, I've done that derivation in about 3 minutes. Okay, good for me. I looked it up in a book. It took people very many years to arrive at this relationship, looking at data and thinking about how waves transmit. Again, other ways exist of deriving this equation. This is just one way. The essential thing here is that velocity of the waves is linked to material properties such as strength and density. If you understand this, the rest of this talk is remarkably straightforward, remarkably easy. If we have a look at a stress-strain curve, and here we have a stress-strain curve, the curve B is using what is called true stress, true strain. That's a term that physicists use to say it's the size of the sample is the size of the sample now, and that size of the sample now changes with time because I put a load on it. And the line A is the same actual data, but presented as engineering stress and engineering strain. Engineers build objects of certain dimensions, and they like to know how those dimensions change. And their point of reference is the original length of the material. So what we have here is the same data, 2 slightly different representations. Be aware of that when you're reading the literature. But what it's saying is the gradient of the stress-strain curve is the strength, and the strength is related to the wave speed. So in the elastic region, up to the point mark 2 on these graphs, where the material is behaving in an elastic fashion, the wave speed is actually constant. The gradient is constant, and the gradient is quite high. It's a high wave speed. But when we start to move into the path after the elastic limit's been reached, what we find is the gradient is lower. So what this says is if you have a plastic wave and an elastic wave, so the material has stress going through it, and as part of that stress associated with elastic deformation, and as part of that stress, the higher stress is associated with plastic deformation, then in these type of regimes represented here, the elastic waves will move faster than the plastic waves. Okay, so that is a way of representing it. Again, other versions of this explanation exist in the literature, but this is a version I use because it's fairly straightforward. So traditionally, we use 4 wave speeds: longitudinal, transverse, bulk, and we have constants, sometimes called Lime's constants. You can read about those in the literature, which help us define it. But the main thing on this slide is to know that the longitudinal, the transverse, and the bulk wave speed are related to one another in the simplest form via very straightforward equations. These show it. Now, we shouldn't be surprised that the bulk wave speed squared equals bulk modulus divided by density. That was the thing we derived a couple of slides ago. But the other ones follow a very similar process. The one thing I point out to you at the bottom is a wave speed in the rod. A rod is the Young's modulus, E, divided by the density. Not surprising, Young's modulus was worked out by looking at loading on rods. So it's not at all surprising that the wave speed on the rod is defined by Young's modulus. Now, in our field, when the stress wave reaches an interface, there's a balance between the two materials. Part of the energy or stress is transmitted, part of the stress of the energy is reflected. And this is an issue of conservation of momentum. So we have waves reach interfaces. Some of the way energy is sent through, some of it's reflected. What is the controlling property? It's a thing called the acoustic impedance in the elastic regime. And the acoustic impedance is the density multiplied by the sound speed. If you want to try and rationalize what this means, it's effectively the mass per unit time you can put into motion. And it is a material property. Density and sound speed vary from material to material. So acoustic impedance controls the transmission at interfaces. Now, there are 2 limiting cases. 2 materials have exactly the same impedance. That implies that you get 100% transmission of stress through interfaces and 0 energy reflected, or the materials are completely mismatched, meaning one of them has either infinite or 0 acoustic impedance, extreme limit there. In that case, 0 energy is transmitted and it's all reflected back at you. So in practical terms, what is a complete mismatch? Well, it's a metal surface contacting a gas or a vacuum. What's an example of something with the same impedance? Well, it's the same material. For example, a piece of metal plate in contact with a metal plate of the same material. It also happens that gold, as in the precious metal gold, and diamond, as in the form of carbon, people seem to pay a lot of money for. Gold and diamond actually have very, very similar acoustic impedances, which means it is very hard. An experiment, don't try this experiment at home. It's very hard to get a diamond to jump out of a gold ring by hitting it, because there is no wave mismatch at the interface between the diamond and the gold. Just a little fact there. So as well as transmission and complete transmission, complete reflection, you can have some defining equations, and these are given here. T is the amount transmitted. It depends upon a force, a stress wave going from material 2 into material 1. Okay, the amount transmitted is equal to this term here. It can be worked out by conservation of momentum. It takes a couple of pages of A4 to work through this. Again, not terribly difficult. The amount reflected is dependent upon the difference in impedance. But if you think about say a polymer metal interface, well, a polymer has a low impedance. I'll say that in a lot of these talks, and the metal has a high impedance. What does a negative reflection coefficient mean? What it means is that something which was originally a tensile style wave, something that is reducing the stress in the system, is reflected as a compression wave, so it changes phase. Hopefully people are familiar with reflection at interfaces and realize that sometimes you get changes in phase of light, changes in phase of stress waves when things are reflected from interfaces. And basically this is assuming normal instance of the wave, so the wave going straight into the surface. And the relationship between stress and particle velocity in the system, which can be derived in a shockwave lecture, which I can't give. The defining equation here is change in stress equals density times sound speed times change in particle velocity. Particle velocity changes at the interface, changes due to transmission of energy through the material. So the change in stress equals density times sound speed times change in particle velocity in the elastic regime. And when I go into a shock regime, when I go to very high pressures, then the sound speed of the material changes. And that means that that term C stops being C and becomes something more complex. Not generally very much more complex, but it becomes a term that becomes stress dependent. But simple equation, change in stress equals density times sound speed times change in velocity of the particles in the material. And that means you can start to track what's happening at interfaces and what's happening within materials. So, dynamic testing of materials. I've set up some basic concepts there, hopefully very straightforward for you. Revision, you probably tell me that you've done more complex analysis, and you're absolutely right. Okay, dynamic testing of materials. So it's the 19th century. People are building bridges and trains. They're building metal structures. They're developing engines. High loading rates on materials become more common. And also, people have greater control of the materials they are using. They're using engineering materials. They're using motors. They're using cutting machines, etc. So dynamic response of material becomes important. So this gentleman here is John Hopkinson, Professor of Engineering, University of Manchester. And he had an experiment where he had a wire suspended between a flange, a weight at the bottom, and the ceiling. And the wire was about 10 meters long. And he had an annulus. This is this kind of cylindrical thing in the middle that he used to drop along the outside of the wire, and it hits the weight at the bottom. And what he discovered doing these types of experiments on wires was the failure of the wire does not depend upon the kinetic energy or the mass involved, but it was very strongly dependent upon velocity. Yes, you could put a static weight on the system and break the wire. Absolutely correct. But if you're doing a dynamic loading, velocity turned out to be a key component. And what he discovered in more detail was if he dropped the weight from a very low height, the wire didn't break. Absolutely fine. It's within its elastic limit. It's within its normal strength. If you hit it very hard, it broke instantly, and it broke at the bottom of the wire. But there is a range of energies where the wire breaks at the top or the bottom of the wire. So there is this intermediate range where you cannot say in advance where the failure will occur. Hit it very hard, the wire will break at the bottom. Slightly less energy, top or the bottom. So this got people thinking about waves moving through materials. This is a very key experiment in starting this field. So basically, if you've got a weight hitting the bottom of the wire, then it puts the wire into motion. And so the stress you're developing will be density of the wire, the sound speed in the wire, which we know is related to Young's modulus, and the velocity of the particles within the wire. So the stress developed was equal to rho density CV. When that wave gets to the top of the wire and reflects from the ceiling, it comes back reinforced due to a wave reflection, due to the impedance mismatch at the ceiling. Basically, the ceiling, you hope, doesn't move very much. It's very rigid. That wave comes back reinforced, and the reflected stress is approximately doubled. Not quite 100% doubled, but certainly 99% doubled. What he also discovered is the dynamic failure stress with this loading was much higher than the static failure stress. That was a key discovery. So velocity is important in the failure of materials, and dynamic failure happens at stresses which are higher than static failure stresses. This is the foundation of this entire field. People in later years studied materials at different loading rates. So here I have a graph. It's log of loading rate, epsilon with a little dot on top on one axis, and stress in gigapascals is on the other axis. And what we see here is a very standard relationship that when you're going from strain rates of -4, quasi-static creep loading, when you get to strain rates of round about 0, that is a kind of standard mechanical engineering laboratory test that you would conduct on materials. The failure stress is kind of constant. It increases ever so slightly with strain rate, but it's not a huge dependence. However, when the strain rates got in the region of 10 to the 3, 10 to the 4, there was a big increase in the failure stress of the material. There were two reasons for this. Number one, inertia. Inertia becomes important. Inertia acts to maintain the material in its shape. So inertia has the effect of apparently increasing the strength of the material. But also there is another more profound thing occurring, which is when things break, they tend to break via low energy mechanisms. Low energy mechanisms generally take a long time to occur. But if you're hitting something really quickly and you're putting a lot of energy into a system, you are accessing higher energy, faster occurring failure processes. What this means is that thing will break, but you need to put in that extra energy to get it to break within a certain time scale. So this means with increased strain rate, the failure stress or the yield stress of the material increases. So this graph shows that 10 to the 3 and above, there's a big change in the yield stress of the material. What is a strain rate of 10 to the 3 in the real world? Strain rate of 10 to the 3 is 2 cars impacting one another on a road. It's a lower strain rate than a bullet hitting a window, but it's very similar. So these are impact events. These are explosions, dynamic loadings, blast waves. This graph indicates that materials will behave differently under those kind of more extreme loading conditions than they will under quasi-static loading. So this graph here, this little table here shows you strain rate versus strain rate regime, going from 10 to the -8 to 10 to the +8. And there are versions where people use laser-driven loading, which I won't discuss, but it's definitely out there, definitely well known, where you get strain rates of 10 to the 10. And what we have here is a rough division between creep stress relaxation processes, quasi-static processes, dynamic processes, which tend to the 1 and above, Hopkinson bar, Taylor impact, which I'll mention in a little bit more detail, ultimately going up to regions where the sample basically doesn't have time to respond in a homogeneous fashion. The system becomes very much wave dominated, and that's investigated in the shock regime. And you can see at the bottom, inertia is negligible at low rates, increasingly important as you go to those higher rates. So John Hopkinson, unfortunately, died in, as is indicated here, 1899. He also died with his older son and a number of daughters. They were walking in Switzerland, and unfortunately, some part of the mountain fell upon them and killed them. So because of this, the Department of Engineering in Cambridge wanted another professor of engineering. So they chose John Hopkinson's son, his second son, Bertrand Hopkinson. So this is Bertrand Hopkinson, and he again looked at dynamic loading of materials. And he came up with this really fascinating device. This is his first Hopkinson bar apparatus. And what it is this shows a drawing of a T chest, so a wooden chest, D. There is a rod of material, B, and there is a little extension to that rod, C, and A is a detonator, or it can be a bullet impacting it. And you can see around that rod, there is a piece of wood, and that leads off to two benches and a couple of rods with pencils on them. And you can also see the wall of the building at the back, and there is another rod with a pencil on it, and that's attached to a piece of paper. Very simply, Cambridge University Engineering Department, Bertrand Hopkinson, measured the shape of pressure pulses using this apparatus, because that little block of material C, he can change the length of it, and he can trap different amounts of momentum, different amount of energy by changing the length of that momentum trap. And this is well in advance of using strain gauges. What he does is the impulse, the impact at point A causes that momentum trap C to jump off the end of the rod into the T chest D. The T chest D is suspended like a pendulum, and it moves because of the energy delivered to it by that momentum trap. And the amount of movement depends on the energy trapped in the momentum trap. So by looking at the length of the line drawn by the piece of paper, drawn on the piece of paper by the pencil attached to the wall, he can measure the energy trapped in that momentum trap. He can vary the length of it. What he is capable, or what he was capable of doing in 1914, was measure the pulse shape in a rod with microsecond resolution using a T chest, a pencil, and some paper. This is, I think, marvelous. This is wonderful. And people used other forms of apparatus, other forms of diagnostic. I love this equipment, but it's not really practical for fast experiments, but still very good. Strain gauges and strain gauge amplifiers came along in the 1930s and 1950s. They help a lot in making this world work a lot more quickly. So this is the original split Hopkinson pressure bar developed in 1949. Same idea, but it's split because the specimen material is now put within the bar as indicated. This was developed by Howard Kolsky at a company called Imperial Chemical Industries in the UK. Now, one thing that was discovered is that if you send a stress pulse down a rod, it disperses. And this means that you go from a nice rectangular kind of pulse to something with oscillations. These are called Ochammacree oscillations. It's because stress can go straight down the central axis of the rod, or it can reflect from the sides. There are quite well developed mathematical expressions to explain the shape of those pulses. They are quite complex. You can read them in Kolsky's book on stress waves in solids, if you like. Pockhammer and Cree wrote this theory in the latter part of the 19th century. That shows real data. So the undispersed pulse is the blue square, the blue rectangle. Real data gathered from a real rod of material using a strain gauge to measure the signal in the strain gauge with time. That is the more ramped dark line with the oscillations on it. It's an effect of the shape of the material. So here's a complication. The signal we get is dependent upon the material shape. And here we have an example of what happens if you let a wave oscillate backwards and forwards up and down a rod of material. In this case, an Inconel, it's a form of steel, an Inconel bar. And I've just overlaid the pulses here. One, the incident pulse, the reflective pulse, the pulse after it's been reflected twice, 3 times. And what you see is basically, yes, the detail of the shape changes, but the average level of the force is pretty constant. So this means you can reflect waves off interfaces, and there will be differences in the detail, but in the broadest sense, the sample will, the stress level recorded will be the same. So I'm getting on towards the latter part of the talk here. You've listened to me talk quite a lot. We're going to show some movies shortly, but this is a Hopkinson bar in real life. It's a striker bar. There's an input bar. That's where the pulse is transmitted down from the impact onto the sample. The sample's that red square of material. That sample gets crushed. It transmits some force into the output bar, and some pulse is reflected because there's an impedance mismatch. That's why I wanted to talk about impedance at the beginning of this lecture. An impedance mismatch occurs. Some of the force is transmitted, some of the force is reflected. Down below, you have the first gauge. The first gauge is on the input bar. Initially, that nice input pulse comes in. It compresses the bar. You get a little bit of Ochammacree oscillation, returns up because the pulse has a certain duration, goes through, and you get the reflected pulse coming back some time later. On the output bar, the second gauge, you get that compression. So here's a movie showing a Hopkinson bar in normal operation. Here you go. That is it. That is your experiment. You can see pulses oscillating in the bars. You can see the sample gets hit multiple times. But what we're interested in this system is that first compression. Now, that is most of the data. That is not what you're interested in. All of this bouncing around complicates the analysis. We're not interested in that. Hopkinson bar theory was to develop a very simple expression for specimen stress and strain in terms of signals from the gauges. And basically, this is the theory. I could go through it in more detail, but I'm just going to say the main thing is stress, strain, and particle velocity are linked by the equation stress equals density times sound speed times change in velocity. Sound speed is related to strength. Strength is related to strain. That is it. If you understand those, you can do this derivation in a very straightforward fashion. You can look it up in a number of books. For the purposes of time, I'm going to skip this part in going through it in detail, but I'm happy to discuss this with people who are so interested. Fundamentally, the strain rate that you record in the Hopkinson bar experiment depends upon the reflected pulse, because the reflected pulse gives you information on how much the bar has slowed down, and therefore how fast it is compressing the sample. And the strain that the sample is experiencing is strongly connected to the amount of force that the sample is putting onto the output bar. So the strain rate you measure on the input bar using the reflected signal, and the stress you measure using the transmitted signal, making a very big assumption that the sample's specimen volume remains constant. And we also, looking in more detail, realize that this sample stress increases in steps. There are wave reflections occurring within the sample. Stress takes time to transmit. A wave speed in a piece of metal, say 5 millimeters per microsecond, 6 millimeters per microsecond. So it takes 2 microseconds for a wave to go through a 5 millimeter piece of sample and be reflected and come back to the input interface. So things take time. So this is showing how it takes. Wave reflections occur, stress increases in steps, and the wave builds up. And you can make a prediction on that, and you can try and measure for a long sample how long the pulses will take. And the prediction means that I got a piece of paper, a piece of graph paper. I did a very simple calculation. I assumed velocity was constant, and I drew that red line. And the real data came back as the Ochammacree influenced black line. And for something that took me 5 minutes to draw, it's a pretty good agreement. If you wanted more complex agreement, again, lots of publications in the literature. However, we've got to take things into account. If we make big assumptions, then other things can occur. We can assume that the analysis is simple, but we've got different equipment. We have different sample preparations. We have different materials which give us different time until the stress in the sample has equilibrated. We've got inertia, we've got friction. All of these things can change. So what does that look like? Well, we can never perfectly align bars. We assume that the gauge sees what the specimen sees. More or less, that's correct. We assume we know when pulses rise. That's another assumption we're making, so that we can align transmitted and reflected pulses in terms of time of behavior at the sample. Those gauges are remote from the sample. We have to move the time basis to say what we believe is happening at the sample. And we got dispersion as well. So we cannot measure, say, Young's modulus using Hopkinson's bar, but what we can measure with great accuracy is the flow stress. So it's a particular tool for doing strain rates of 10 to the 3, 10 to the 4, and the flow stress is measured accurately. Seen that one before, Ochammacree, undispersed pulse. So a simple analysis is like the red line. A complex analysis can reflect the more detail in the data. But if what you want is the flow stress of the material, when is that signal nice and flat, you can just draw that line straight through those oscillations and get the flow stress with great accuracy. If you've got two samples of an identical material, but you put different surface roughnesses on it, so the way the beginning of the stress rise is affected by that surface roughness, you will get those two different angles of stress strain at the beginning. But the flow stress, when the material is moving sideways, as you see, the top of those lines match quite well. So Hopkinson bar, a lot of discussion, but flow stresses measures really well, really accurately. We can discuss friction and inertia. We can talk about changing temperatures. There are a number of factors to take into account. If you're worried about friction in your sample, I would say do the experiment without lubrication, do the experiment with lubrication between the sample and the bars. See if there's a difference. No difference means friction isn't a big effect. It's pretty straightforward. And here are some high-speed images of a split Hopkinson pressure bar. The blue dots indicate the images, but I'll show you a movie. The movie is far more informative, and it tells you what's going on in a very straightforward fashion. If you make an assumption that your sample is deforming uniformly and evenly, and friction and sample shape are having no effects, you could go horribly wrong. So here's the movie. What were these slides about that I flicked over so quickly? Basically saying that sometimes it takes time for a sample to get into stress equilibrium. We can discuss that later. Sometimes you get very poor sample transmission. Yep, signal transmission. Yep, got to be careful. Sometimes you don't know when the stress rises. I know the stress started to rise. There's a curve there. When did that curve start? Don't really know. Have to go work it out. How does stress move? How does the stress speed move through the sample? In this case, for long polymer specimens, it was discovered that on the first pass, the wave speed was quite high, but it slowed down on subsequent passes because the first pass through that polymer sample was affected very strongly by inertia. And the inertia made the material not want to move laterally, which meant the energy had to go along the sample. And because the energy is going along the sample, that means that the wave speed we see is higher, because wave speed, sound speed, is related to the amount of energy you put into the wave. Here's a movie. This will show a lot of what I've been talking about in a bit more detail. So long bit of sample, I'd say, don't too long. Oh, look, is that even deformation? No, it's being quite badly affected there. Those lines are just drawn on the sample to give you an idea. So let's play that again. So there's your sample. As you see, there is more detail going on there than a simple equation will predict. So having diagnostics like high-speed photography helps us immensely in looking at the detail of the system. So is there an upper limit? Yes, there is an upper limit for Hopkinson bars. You can hit the sample so hard that you damage the Hopkinson bar equipment. The bars become plastic, and inertia has an effect as well. So there's a paper by a gentleman called David Gorham. I will supply Oleg with a copy of it. He will share it with you, I hope. And we can talk about the effect of inertia on the samples you read. Now, the next part, the final part of this presentation, is about Taylor impact. Here's G.I. Taylor, Jeffrey Ingram Taylor. Those are his dates of birth, date of death. And he has very famous, worked on the Manhattan Project, on the development of the nuclear weapon, did work on seismology, a lot of very wide range of subject matter he covered. And he developed a thing called the Taylor impact test. And it was a simple test developed to look at different types of armor, steel armor, during the Second World War, or the Great Patriotic War, depending which country you come from. And it involved firing a cylinder at a rigid target. And so let's have a look at what the experiment looks like. So on this side of the screen here, we have a rigid target, and this is a bar that's being a rod that's being fired at that target, and this is fired about 100 meters a second. So the rod goes up to the thing, impacts it, and deforms on the surface, and then eventually it bounces off. So I'll play that again. So this is the impact of, in this case, a copper rod on the surface of the material. Okay, there it is. Fairly straightforward, I hope. And what we're doing, we're firing a rod at velocity u at the surface of a target. It's got an initial length of rod, L0. We send a elastic wave, which moves quickly through the material, and we've got a slower moving plastic or deformation wave behind it, moving at a velocity v. That elastic wave reaches the rear interface of the rod, reaches the back of the rod, and is reflected. Now, I mentioned impedance differences and change at interfaces. You look at that and consider it and think about it. What is the change? Well, the rod is slowed down, and the amount it's slowed down is twice the stress associated with the elastic limit, the yield stress, divided by the wave speed on the rod and the density of the rod. So that simple equation, the simple John Hopkinson style equation, is useful in describing this dynamic event. So that wave goes back, it meets the plastic wave. What does it do with the plastic wave? It interacts with it, it takes away stress, it slows that plastic wave down and eventually stops it. You're left with one part of the rod at a certain deformation, another part of the rod at a very strong deformation. And that is, here we have 3 examples of Taylor impact specimens obtained at different velocities. Now, the shape is different because the strain rate was different. Yield strength depends upon strain rate. So I hope that you can see that we're talking about elastic waves, plastic waves. We have wave reflections at interfaces. We can make very simple assumptions. We can make very complicated assumptions. But ultimately, it's reflection of waves at interfaces which becomes important. Taylor's analysis was not particularly complicated. Yes, it occupies pages of a journal article, but it was approximate, and he always recognized it as that. You can do a thing called symmetrical Taylor analysis, where you have we have a rod hitting a rod of the same material. That is useful for two reasons. Number one, if you're doing modeling, the center of mass of the experiment is always between those two rods. And also, as the rod deforms and spreads outwards, the rods expand at the same rate. They're the same material. So friction doesn't have any effect because they're moving outwards at the same rate. There's no friction between them. Simpler arrangement in terms of analysis, a little bit more irritating when you come to set it up. That's a high speed for photographic sequence, but I'll show you the movie. This is what a symmetrical Taylor impact looks like. Rod comes in, hits that rod. You can see the bulge building up. You can also see the top and the bottom of the rod behave slightly differently. That's because of this wonderful support here. It was one of our early experiments. Afterwards, we discovered, like Bertrand Hopkinson in 1914, it was easier suspending our samples from wires. So that was an early experiment, but gives you an idea of what a symmetrical Taylor test is like. People tried to model this, and Ronald Armstrong and Frank Zarelli came up with a model for the deformation of iron using dislocation mechanics. So now we're bringing in some microstructure, some mesostructure, some crystal-sized structure. We're bringing in dislocations into our model. We started to use dislocation mechanics. This model is quite widely known, and it was very good at predicting the shape of that rod, shape of a rod like that, what the shape of the sample is, and you could compare the diameter of the rod with distance along the rod. The dots are the experimental data. The black line is the prediction from the model. It looks pretty good. You can go home and say, I'm happy, I've explained this data. Okay, let's not do iron, let's do copper. Copper, okay. So the diameter of the rod is, it's got this bulge in it. It's got this bulge in it about 2/3 of the way along. The diameter is quite big, and then that bulge shrinks. And the model says it should just expand in a monotonic fashion. Actually, something else is happening. Here, we're getting onto what's going to be a theme that I will be bringing up again and again through the rest of these presentations. Iron and copper have different crystal structures. This means the way they deform is ultimately linked to, in copper's case, the history of the mechanical treatment of that material. Now, steel properties depend upon mechanical treatment as well, but copper has a much stronger memory effect, work hardens. There's a whole bunch of effects because of the crystal structure of the material. And this leads on to the increased level of complexity. Simple models give simple results. And if you want to match things more or less okay, that's fine. If you want to do things which are more complicated, then you need a lot more effort. So what's my conclusion today? Well, material behavior changes with strain rate. Inertia is a big effect. Failure processes take time. There are a range of platforms that are being developed, often with a simple analysis based upon isotropic strength and a failure, sorry for the spelling mistake there, a failure-free model. And it's a good first level approximation. If we want to improve, we have to bring in extra diagnostics, and that's going to be the subject of the next two presentations I'm giving. Okay, at that point, I will stop and I will cease to share the screen and look at myself because I think that's too much. There you go. Back to me. Okay, I hope you found some of that interesting, and I hope that hasn't bored anybody too badly. Oleg, if there's any, I've got a short period of time, but anybody want to ask any questions?
Bill, thank you very much for excellent presentation. And may I ask colleagues to have the questions?
And they haven't. And don't be afraid to ask me questions, because I ask very silly questions on a regular basis, okay? And sometimes I ask intelligent questions. It doesn't matter. Don't be afraid to ask. And Oleg, please tell everybody that they're welcome to email me if they have questions they want to ask.
Okay. Okay. Bill, when my colleagues are thinking concerning questions, may I ask you opinion? Because I'm sure that in the future we'll have also opportunity to discuss this. But it's very important questions for us, and I think for Shockwave society. When you're talking about a dynamic and shockwave response of materials starting from strain rate to 10 to 4, 10 to 5, when we have a very sharp increase in the stress versus strain rate. What about your opinion concerning universality of these asymptotics registered by Swiggle and Grady as the 4-power law? And also in the links with Armstrong's linear models, because I think from point of view of dislocation kinetics, I think it's one of the best model which clarified plastic response of material in the links with dislocation dynamics.
Yeah. So this, so Oleg is absolutely correct. Dislocation dynamics, Armstrong's Zarelli model, very widely used, very important. The Swiggle-Grady relationship, that the stress you get to is related to the strain to the power of 4, if I remember in the correct format. I sometimes get it wrong. Actually, it's 4 for metals. If you have granular materials, that power index is 2.5, thereabouts. It changes with material type. So the Swiggle-Grady relationship is a great, what I'd say, empirical relationship. And it's actually a question I often, I've tried to get some master's students to go and kind of write a review on the Swiggle-Grady relationships. I think everybody avoids it because they find it too complicated, because the explanations are very, can get very complex. But Swiggle-Grady showing stress strain rate relationships is another fundamental law, fundamental thing in this field, but linked to dislocation mechanics, linked to mechanical structure, but it's not 100% clear if you could predict that indice on the strain rate. Stress equals strain rate to the power 4. Some constants are attached, but could you predict that indice, that power 4 of 2.5 in advance? That's a question I'd very much like to understand in more depth. It's something I personally haven't read in a great deal of, but I'd certainly like a master's student to write it up and tell me the answer. I would be delighted if that could happen. I hope that doesn't sound like too much like me avoiding the question. It's a very serious question. It's just that I think the answer, I'm not capable of giving people in-depth explanations, but it is a key question in the field.
Mm-hmm. And Bill, thank you very much for your opinion. I think for future, in the framework of our projects, it will be one of the most important questions, because this asymptotic response that probably could be observed also in liquids, because we plan to realize and to continue experiment for shock loaded liquids, and also concerning hydra and sonoluminescence. According to our feelings, maybe we could clarify these similarities with plastic response of materials such as shockwave fronts. Thank you.
Can I just say I'm very sorry. I've got to go give a tutorial to some students now. I apologize for that very strongly, and I would never wish to be rude, neither to my students or to your good selves. Oleg, our next meeting is on Monday. Is that a correct statement?
Yes.
Mm-hmm. So can I ask yourself and your colleagues, if they want to send me an email with some questions, I will try and answer before the next meeting. I'll give it a go. But I'm happy to. This is a conversation we need. And today, I just wanted to set the scene. Hopefully, I've done that. In the next meeting, we'll talk about some diagnostics and trying to take it forward and give more time for discussion, because we have the basis of the way I consider things established.
Okay.
So can I thank you?
Thank you very much, Bill, again. It was an excellent presentation. It's really pity that for our team it was too late. I think if it could be, for instance, several years ago, I think it would be very, very nice.
Oh, well, yeah. No, it's time is nobody's friend.
Okay.
I'm not in straight studies, that's for sure.
Okay, thank you very much, Bill, again.
Thank you,
all
sir.
the best.
Have a wonderful weekend, everybody. Okay.
And for you also.
Thank you very much for the lecture.
Bye.